basically, some of you might remember, I think Camila was back there, at Science Polish Perspectives Berlin last year, definitely the best edition of Science Polish Perspectives, hopefully until now. Oh, things disappeared, now we are here. And I talked about the vaguely successful part of my PhD. So I talked about the vaguely successful part of my PhD, and you all know that it's like buses, you wait forever, and finally they arrive. So that was more or less what I talked about, a couple of papers and my thesis. So that was year 2018 when I presented all of that. And then I realized, well, what happened in all of those years before, when I started my PhD in 2014 and I finished it in 2018? That was a big unknown. And we already saw pictures of nice synthetic setups. That was more or less what I was doing on a lucky day. And that was one reaction. That was actually pretty. Most of my time during my PhD was blood and tears, and everything was horrible. So basically, I felt like I wasted 4 years of my life to get a couple of things. So the two papers I talked about, they report around 20 molecules. 20 molecules equate to around 4 years of work. And my question is, do you know how many molecules we can actually synthesize? We can synthesize a lot of molecules. That is a very big number, 10 to the 20-something. And this is the kind of lower bound estimate of how many drug-like molecules there are in the universe, that we can synthesize. These are not possible molecules. These are just ones that could potentially behave like drugs. And if you don't know big numbers, and I don't, and Janina doesn't either, that's more than there are atoms in our visible universe. So basically, we can synthesize probably, or we could think of, more molecules to synthesize than there are atoms available ever, which is already quite scary. So we should try and predict which ones are actually useful, which ones we should waste our time and effort synthesizing. I mean, 4 years of my life produced 20 molecules. If all of them are wasted, that's wasted 4 years of my life. It's wasted synthetic efforts, that's wasted material, wasted energy, and basically huge waste that we should not afford in climate emergency kind of status. So that shouldn't really happen. So let's predict. I mean, there is this big thinker, Cristiano Ronaldo. He says, there is no point in making predictions. And it's not worth speculating because nothing is set in stone and things change all the time. Luckily, he said in football. Because there was another thinker who basically said, I do not fear computers, I fear the lack of them. And that is an area that we all believe, in my field, that computers can solve. So now we have a lot of computing power, we can do a lot of things, and we can try and predict properties of molecules before we actually go to the lab to synthesize them. So we basically can tell you, out of these 10 to the 23 molecules, you should make this one that's going to save the world, cure cancer, and do everything else you wanted to do. Just focus your efforts doing that, spend 4 years doing one useful thing, not like me doing 20 useless things. So what should we target? What my work targets is things that we call porous organic cages. They are quite fun materials. So these are all just kind of simplified crystal structures of things I did not synthesize, but people did. And that pointer does work. Oops, that pointer does work. So basically, they all are molecules with a hole inside. That's why we call them cages. They are big enough to encapsulate another molecule inside of what we would call their inner cavity. Why would they be useful? I mean, apart from the fact that they're super pretty, and I like making pretty things, sort of tetrahedra or these massive things that I don't even know what it would be called like, or kind of weird, wonky, double cavity shapes. They're all really cool, but they have uses. They are actually found useful. And what they do is they pack very inefficiently. So you have one molecule in solution, and you try to make it into solid state. So you'd crystallize it or deposit in some other way, and they would pack. I mean, as you could see, I'm pretty bad at making pretty pictures, so I stole that from Andy Cooper. That's a really good picture. They can pack in a low density state or a higher density state or a kind of completely amorphous state. And that is really interesting because what is shown in yellow here is the channels that are available to molecules in the solid phase. So basically, our cage has a hole inside, and another cage next to it in the same material has a hole inside, and these holes are interconnected. So you basically have like a cavity channel, tunnel, pore, as we would call it, going through the molecule. And we can tune them. So we can tune the shape of the cage. That would tune how big or small the cavity is, how big and small the windows are, and how well they pack. We can tune how well the materials pack into solid state, so basically if there are any pores between the cages or not. So for example, the same cage here, crystallized in different ways, was either porous to both hydrogen and nitrogen, because it has this massive pore between cages that were packed very loosely, or they were packed quite tightly and they had no interconnected channels, so it was not porous to anything, not even a hydrogen molecule could go through. And this was porous to hydrogen, but not big enough to be porous porous to hydrogen, but the holes, the tunnels were not big enough for nitrogen to go through. Nitrogen is only slightly bigger than hydrogen. So that is quite cool, because it's one the same cage that can be used to separate different things. Even more surprisingly, I don't have it on a slide because it's a very recent paper, they are able to separate deuterium D2 and H2. So basically, the exactly same electronic kind of things. They differ by 2 neutrons, 1 on each hydrogen. And they are able to separate a gas that has a mixture of those using those cages. And to those of you who went to SPP Berlin last year, the keynote mentioned that distillation processes, so mixture separations, are like a large proportion of industrial process greenhouse gases production, which is quite a bit when we try and tackle climate change. So all of those things, they could act as membranes and do separations based not on boiling temperatures, but simply on the difference in shape. So things are like that, and things like that, that would be similar, but things like that and things like that, they could boil at the same temperature, but they would not be able to go through the same pores. So at room temperature, we are able to separate them, and that is great for industrial processes. So it's membranes, mixture separations, catalysis, all of those different things that you can do. And all I showed you before was kind of general introduction, and I'm now going to have 20 more slides with boring results. But no, because I don't want to show you any chemistry. But as you saw before, all of these cages, they have spherical cavities. So they have the same ligand, as we would call it, assembled into a structure. And that would be really cool if we could tune the shape of that. If not have the same ligands, but have mix of different ligands, but in a precise, well-defined way, give us a well-defined structure. So we tried with our experimental collaborators to mix different aldehydes, so different precursors for the same cages, and they could, in principle, either separate fully into 2 completely distinct cages, or mix into some sort of weirdly funny cages, and there's great nomenclature for that. We call it narcissistic and social, because they don't mingle or they do mingle, or they can just form a complete random mess. So just to show you that predictions sometimes work, we applied a workflow that is reasonably crude, but decent enough to give you pretty decent separation of energies between the different cages. So basically, we look at what the molecule would look like on its own without even looking at the whole packing in the solid state. We try and identify what we would call conformers, so arrangements of molecules that are not isomers, but they're kind of differently shaped. We would do some optimizations, we'll calculate energies, and to our surprise, the lowest energy structures were always the ones that were observed experimentally. So that is a way that computational prediction, in this case, could aid the development and design of a material of well-defined porosity, of well-defined structure that was not earlier available. Because you can't just mix everything at random and hope for the best. You can see that is quite a slow process. It takes hours or days, so not really great for high-throughput screenings. But we do have this piece of software in the group called SDK, which stands for supramolecular toolkit. And supramolecular chemistry is cool because you tell people, I do supramolecular chemistry, so they think it's super. That assembles molecules in milliseconds. And we can then do simulations in minutes to kind of at least assess whether the structure would have a persistent inner cavity or would be just totally scrambled. And that is viable for high-throughput materials discovery. So what I didn't want to go through, but what I should mention because it's 21st century, we do all of these cool things like, neural networks, machine learning, data science, big data, and other stuff to basically automate that process, apply genetic algorithms, and find the best possible candidates of what people should synthesize. So that's kind of like, watch this space. And with that, I would like to thank mostly my boss and the entire group. And I was told not to thank every single person in the world. So these are them. I would like to thank my parents, you. Thanks for the invite. And if there are any questions, I will try and tackle them.